In this video, we're going to discuss what determines whether two figures are similar. And typically we'll just focus with polygons, triangles, quadrilaterals, and so on. But for a quick example here, we have a case of a model home and using the model to determine how large the full-size home would be based on the dimensions we're seeing here, and knowing that in a full-size home, the door is typically 6 feet 8 inches tall. And so what I've done already is I've set up a proportion, because if two figures are going to be similar, if we take this model home and create the full-size home, we'd expect the full-size home to look just like this one, but on a larger scale. Meaning we're going to increase all the sides, all the dimensions by the same amount. And an easy proportion can solve for us how long the porch would be on the full-size home. As long as we're consistent here, and you can see one way to organize this would be put your model values in one fraction of the proportion. So what I've done here is, for the model, I've put the height of the door and the length of the porch. And as long as I do that same thing over here for the full-size home, we can solve. And so for the full-size home, I followed suit. I put the height of the door over the length of the porch, which we're going to find, and that's why I put X. And you can also notice I converted everything into the same units for ease of finding our solution. So as far as solving this, we can cross multiply and we get 3x equals 720. And dividing by 3, we'll have x equals 240. Keeping track of our units here, this would be 240 inches, which, if we wanted to convert to feet, which would be more common, divide through by 12, x is 20 feet. And so this is just one isolated example of how similar figures could be used in the real world, as we call it. And what we can do, instead of just using proportions all the time to solve, another question that's posed here is there an efficient way to convert all of our dimensions from the model house to the full-size house? And the answer is yes. We're going to look into a scale factor. So the question now is there a scale factor? And once we know that value, we can treat this like a dilation, to where we multiply all of the dimensions from our model by that factor to figure out what the dimensions of the full-size home would be. But let's not worry about the scale factor at this moment. Let's figure out a little more about similar polygons, and we can clear up how we can find that scale factor pretty easily. So looking here, let's make a little connection to what we've been doing in the past. For a long time, we've been talking about whether two figures are congruent, and you notice that congruent symbol here. It involves a couple things. It has the tilde up here, and that tilde has a purpose. It means that the two figures are the same shape. So a triangle can only be congruent to another triangle. An equilateral triangle can only be congruent to another equilateral triangle. But with the congruent is more restrictive. We also have this equal sign involved, and that equal part represents the big part of congruence, is that they are the same size. All of their measurements are the same. And that's not where our focus is today. We are saying for shapes to be similar, they're going to look the same. They'll still be copies of each other, except those copies will include an enlarged copy. So they'll be the exact same shape, except one will be a larger version of the other one. And so to represent that, we just keep the tilde, that squiggle. We lose the equal sign, because similar shapes we don't anticipate are the same size. We just want them to look the same, but on different scales. Okay, so to help clear that up a little bit, let's look at this example right here. We have these two shapes. It looks like two trapezoids right here in this diagram, and you can do a visual test and ask whether or not they look the same to you, and you'll probably decide that this figure on the right is just a larger version of this figure on the left, meaning that these two figures are similar because they are copies of each other, but one is an enlarged copy. Now, they look the same for a reason. You might also notice in these diagrams, both have two right angles, both have this obtuse looking angle in the same position, and both have this acute looking angle in the same position. And that is what a key feature of similar figures is, that all of the angles are going to be the same. And actually, that's a big reason of why they look the same. A right angle looks like another right angle. And so when we know two shapes are similar, one big thing we need to know is that their angles are going to be the same. And which angles are going to be the same is based on that similarity statement that we'll see from time to time, just like we've seen congruent statements in the past, where the first letter of this polygon corresponds to the first letter of this polygon. So angle A should be congruent to angle G. Angle C, the third letter, should be congruent to angle I, the third letter. But going back to that visual test, the reason that the angles don't change, you can think of this in terms of zooming in and zooming out on a screen. If you zoom in towards a 90-degree angle, it'll get larger and larger, but it's still going to look like a 90-degree angle. You can zoom in on an obtuse angle, and it'll get larger and larger, but it's still going to be that same obtuse angle. So let's always keep that in mind. These similar shapes where one is just a larger copy, these angles are all going to be the same because through a dilation, we are really just zooming in and zooming out, and all of these angle measures are going to hold true. Now, what won't hold true are the sides. Sides are going to change. If this figure is smaller than this one, then I would expect that side AD down here is smaller than side GJ down here. And it depends on what our scale is, but sides won't be considered congruent. Their measurements won't be equal, but they will be proportional, and that's going back to that idea of scale factor. So just an example, if this side length was 5, and let's say the scale factor was 3, then I would know that my new side is going to be 15 because 5 times 3 is equal to 15. But that's how similar figures are formed, by a scale factor. And since I use a scale factor of 3 there, I would have to use a scale factor of 3 on all of my sides. So if this was 3 and this was 4 and this was 2, I would have to multiply all of these by 3 to get my new side lengths over here. And so there's a way to check to see if we've used a common scale factor throughout, and that is what we're seeing down here when we say sides are proportional. We are checking whether or not there is a common scale factor. So to check for that scale factor, all we need to do is set up ratios of our sides. And right here, you see how it's set up. We're comparing AB to GH, and there's a reason for that. If we go back to our diagram, let me get rid of these markings over here. And if we look at our diagram and our similarity statement, visually, you can probably see that AB corresponds to HG. We get HG by taking AB times whatever our scale factor is. But that similarity statement also tips us off because A and B were the first 2 letters listed, and G and H were the first 2 letters listed. And so that's how I know that these two are going to correspond. Same goes with BC to HI, CD to IJ, and AD to GJ. And so what we're checking when we set up these ratios is whether or not they all reduce to the same thing, because if they reduce the same, that means we use the same scale factor to create each of these new sides. When you do this, make sure you're consistent. You might notice in the top of these fractions, all 4 of these segments came from the smaller figure, and all 4 of the segments of the larger figure are in the bottom. So that might not be too clear yet. Let me show that to you on the back. One last thing before I leave. The reason that there's 4 fractions here is because each of these figures has 4 sides. So we have 4 pairs of sides to investigate. But let's look at an actual example with actual values. So in this next diagram, we see 2 triangles, and you can do the visual test first. Ask yourself, do they look like copies of each other, where one is on a larger scale than the other? And you'll probably say yes, this triangle on the left looks like a larger copy of the triangle on the right. You can also do our test of angles, which says all of the angles are congruent when shapes are similar. So you see they both have a right angle, they both have this angle with the 1 arc on it, and they both have this angle with the double arc. So we do see that they have all the angles the same, meaning they are similar to each other. And we also have the similarity statement to guide us. Now, what we want to do today here is find the scale factor, which is simply what value gets us from one pair of sides to the other. So what value can we multiply by to get from one diagram to the other one? And you could work it either from left to right or from right to left, big to small or small to big. That's just depending on how you see things. But before we can do that, we need to figure out what sides correspond. So looking at 15, two ways to know which side it corresponds with. First, you can look and see it's on segment AB, and then realize that would have to correspond to segment XY, which is here. Another way to know that would be to look at the measurement of your sides. 15 is the smallest measurement in this triangle. 6 is the smallest measurement in this triangle. And so that tells me that those two sides would have to correspond. Okay, and we can use that same strategy throughout. 20 should correspond to 8. So the question is 15 over 6 equal to 20 over 8? And lastly, 25 here corresponds to 10. And so is this also equal to 25 over 10? And again, what we're checking here is whether or not they reduce to the same amount, because if they do, that means we use the same scale factor throughout. So let's go ahead and check this. Reducing all these, you could say it's 5 halves. Dividing both of these by 3, divide both of these by 4, you get 5 halves. And the last one, divide them both by 5, you can get 5 halves. You could also write this in decimal format if the decimal is nice enough for that. Here it's just 2.5. That's pretty simple. So that we're free to use this as well. So why is the scale factor 2.5? That's because you could multiply each of these side lengths here times 2.5 to get these side lengths over here. 6 times 2.5 is 15. 8 times 2.5 is 20. And 10 times 2.5 is 25. Just a note, if you were to flip all of these fractions over, your scale factor wouldn't say 2.5 anymore. They would all reduce to 2/5, and you would end up saying your scale factor is 0.4. Technically, that's based on your comparison, whether you're multiplying the larger values to get the smaller or in the other direction. As far as our class is concerned, both values are acceptable, whether you choose 2.5 or 0.4. So scale factor is very easy to find. You just compare your sides, and whatever they reduce to, that's your scale factor. So a way to check if two shapes are similar would be to check if there is a common scale factor, because if there is, the two shapes will have to be copies of each other, just on different scales. So the question here is whether or not these two pentagons are similar, and we have two ways to check this based on what we've said. Do they have all of the same angles? Well, you can look. They both have right angles, 2 right angles. They both have 2 angles with the single arc, and they both have that 5th angle with the double arc. So the answer is yes. All corresponding sides are congruent. Or all corresponding angles are congruent. Sorry about that. So we know each of the angles is congruent. And the reason, because these are congruent, that's why these two shapes look the way they do. And our visual test tells us that this is a smaller copy of that one if we just reflect it over. But what we need to know is, once you know all the angles are the same, that is a guarantee for similarity. So this guarantees similarity, meaning that we don't have to check anything else. Similar figures have to have the same angles, and that is enough evidence. But if we don't know the angles, we can check for that scale factor with our sides, see if there's a common scale factor throughout. And this one is easy enough to where we can see it. You can see all of these sides here can be divided by 2 to get these sides over here. So we know it's 2, but let's say it wasn't so obvious. What if the numbers weren't so obvious to where we knew the scale factor just by simple investigation? Then what we can do is we can set up those ratios. And since we have 5 sides, we're going to set up 5 of these ratios. So we're going to see 5 fractions. And the question is, do they all reduce the same? And it's your choice. You can either put all of the values from the larger figure in the top, or you can put them all in the bottom. So let's say we put them all on the top, and we have a couple of 12s and a few 18s. And those correspond to the 6s and the 9s over here. So we'll put the 6s under the 12s and the 9s under the 18s. And again, the reason for that is 12 is the smaller of the measurements here. 6 is the smaller of the measurements here. So those correspond. And very quickly, you see that each one of these ratios, each one of these fractions will reduce to a value of 2. And so what that means for us is there is a common scale factor. These shapes are similar because their sides are proportional. So one thing we'll do is we'll determine whether two shapes are similar using one of these two strategies. We don't need both. They both will tell us on their own. Something else we'll do is find missing values like we did with the model home example. So in this case, we have two trapezoids. We're told from the beginning that they're similar to each other. And so because they're similar, we know right away that the sides are proportional. Okay, so looking at our sides, we are going to solve for x here. And we see x is over here on the bottom side of this larger figure. So I'm going to highlight this side in green. And what we're going to see is what we need to figure out is which side in the other trapezoid corresponds to x. Now, visually, you'll probably determine that it's 10. But we don't want to totally rely on visuals. There's a chance that a diagram is not drawn to scale. So remember, the other way to check that is if x was on segment WT, which is the middle two letters here, it corresponds to the middle two letters here, which is QR, which is what we did highlight. Okay. So we also have the task of solving for y, and if you look at this side over here, we have a 3y minus 1, and so then the question becomes, I don't know if I can get rid of that highlighting. The question becomes, which side over here corresponds to 3y minus 1? Is it the 12 or is it the 9? Well, upon further inspection, we don't want to guess here. We look, 3y minus 1 is on side RS, and that's the last two letters of this. And if we look here, WV is the last two letters here, and so 3y minus 1 corresponds to WV, so that would be 12. So now we know 3y minus 1 corresponds to 12, which then will lead us to realize that 6 here corresponds to the 9 over here. So these are things that we need to know. We didn't want to guess on that. We can use the similarity statement to guide us. But remember, if shapes are similar, they're not the same size. They're just copies of each other on different scales. So one of these is larger than the other one. And if we knew the scale factor, that might help us figure this out. But if we don't, then we can set up proportions. So let's say we want to solve for x. And I see x is on the screen side here, which corresponds to 10 here. We can start out with proportion saying that 10 over x is equal to something. And I have some choices here. I can either use the blue pair of sides or the red pair of sides to compare this to. And I'm going to use the blue pair of sides because, as you notice, each of these blue sides, neither one of them involves a variable. So I'm going to set up my second fraction using that 6 and 9. And I need to make sure that the 6 goes in the correct location, needs to be in the top of the fraction because it's in the same diagram as 10, and I put 10 in the top of this one. So this ratio says 6 over 9. We have an easy proportion here. Cross multiply, 10 times 9 is 90. 6 times x on this side, divide through by 6, and 90 equals 15, or x equals 15. Okay, and we can do the same thing for y, which is on one of these red sides here. So we could say that 3y minus 1 over 12. And then there's no reason that you can't use that blue pair of sides again. So let's go ahead and set this also equal to 6 over 9. Okay, and cross multiply as we know how. We'll take 9 times 3y minus 1. And you notice here we're going to have to distribute. On the right side, 12 times 6 is 72. Distribute through, you get 27y minus 9 equals 72. Add 9 to both sides, 27y equals 81. And divide by 27 to get y equals 3. So we use this idea of proportionality. And to see why these values have to be true, if you go back to our sides, we said x is 15. So if I had put it at 15 right here, y is 3. So if I substitute y, I have 3 times 3 minus 1. That would make this side length 8. Our scale factor, you might notice, is based on what we can multiply by to get from 6 to 9 and 8 to 12 and 10 to 15. And it's 1.5. So there is a common scale factor here, and we made sure that was true by using this proportional relationship. So go ahead and try it if you want. Take 6 times 1.5, 8 times 1.5, and 10 times 1.5, and you will get these three values. So keep using this idea of proportionality to keep that common scale factor. Okay, so one last example for us to look at would be another that's based on our sides for similar shapes. So the idea for this last case is if we know that two shapes are similar, that means that their sides are proportional. They're all increased by a common scale factor. Well, if sides are going to be proportional, then any calculations based on sides are also going to be proportional because they also get increased. And one example we could look at is perimeter. And if you think about it, it has to happen because if this shape is a bigger copy of this shape, that means all of the sides are going to be larger, meaning the perimeter is also going to be larger. And so what we can do is we can use this idea of proportionality, a couple approaches here. One, realize that we are looking for the perimeter of this figure, UTWV, and that we know the perimeter of this figure over here because we can add all the sides together. They are 6, 8, 6, and 12, which will give us 32. Okay, so there are a few ways we can do this. One is figure out what the scale factor is because it's more apparent in this one. So if you look closely, you'll see that this 12 here corresponds to the 24 here. We can get from 12 to 24 by multiplying by 2. So one thing you can do is you can multiply all of your sides by 2 to know what the new sides would be here and find the perimeter that way. So add your 4 sides, you're going to get a perimeter of 64. So the perimeter is going to be 64. Now, it's not how we're always going to be able to do it because we're not always going to know all the sides in a diagram. So another option is if you know your scale factor, realize that if the sides are going to be increased by a scale factor of 2, the perimeter is also going to be increased by a scale factor of 2. So another way to get our perimeter is take your smaller perimeter, multiply it by 2, and you get that same perimeter of 64 that we already calculated. But that is only in a case where you have enough information. Let's say we find one last way that doesn't need a lot of information. We can find this using a proportion. Because sides are proportional, calculations based on our sides are proportional, meaning our perimeter can also be used in our proportion. So an option here would be use your corresponding sides of 12 and 24 in part of your proportion and compare that to your perimeters. 32 would have to be in the top of the first fraction because that comes from the diagram with 12. X would have to be in the other position for the other perimeter. And you can cross multiply. You can cross multiply now if you want to. You'll have to take 24 times 32, or you could always reduce the 12 over 24 first. And once again, you're going to notice when we cross multiply, we get that same answer of 64. And I wanted to show you those other strategies first so that you can convince yourself of what the answer is supposed to be. And then we could see that this is a valid method of doing that. So we can use perimeters in our proportions too.